So this is at rest. This wall is at rest. What does that mean? That means all this failed zone out here is at rest. And that's our 7-minute timeline. This is K over here. So it's been crippled along this what do you call it, a plinth beam. You can refer to it as a drop slab. You can refer to it as a 1979, they pretty much call them spandrels. Spandrel looks like this. Spandrel detail. And that was what we look at when we look at the between K, L, and M. K, L, and M. The connection between the two of them. Then our deck comes over. But we have an elevated deck here of 12 foot 9, 11 foot out. And this is 7 foot out. And elevated to 12 foot 9, same elevation. And that's all over here. Remember this, if you followed the video here, the one before, we talk about the ledge over here. I say we, you participate, and how that indicates the shearing action going across. And we need an anchor point. Our anchor point is the wall where it resists. It doesn't just keep going across. This indicates that it went back up and came to a stop. So this shows that the anchor, that it, see the ramped up right here? See the bottom part of that where it connects right here? I'll erase it again. But right about there, it shows that at this nodal area there, if we can call that a nodal area, right here is your hinge. This shows as far as it went at that location with the forces coming this being tugging, resisted here at anchor point, the building. And then on the other side, the anchor point, of course, was this wall system. This wall had a huge tug on it, if you will. It stayed in place, bent some rebar, and released. All right, it released and went down. The stresses I measure is somewhere about on the order of this. It's going to blow your mind. From that wall, coming all the way across, going through the columns either side, about 70 feet. Miami Herald and Dawn L. Lehman's she, her, respecting her Twitter account with identifying herself as she, her. She states that finally it shows it's unlikely that the collapse of the building initiated under Unit 111. So unlikely that it initiated under 111. 111 includes K, L, and M. So she's excluding K, L, and M as the initiating location. This is the lady that says you can't judge a collapse by, figure out a collapse by its failure state. But now all of a sudden she can state that it is unlikely. This is her statement. Her statement. As has been suggested, since the additional structure there protected that area of the slab. So the additional structure there? Well, the additional structure there protected the area of the slab. Okay, she cannot process the data correctly. This video will reveal that. And the previous video did also, just if you know how to slap it together. All right, this current video will slap it together for you to show that this is where her location, what I'm going to state next. Next statement is, it is more likely that the damage to the level 1 slab within the tower, so within the building, not outside the building, that's the tower, propagated north and east from the gym. So she's stating from the corner there, from the gym, and the slab to core wall connections. So she's stating that it's happening from the gym, underneath the gym, over to northeast from the gym. I'm going to show you that's exactly where, unequivocally, it did not start from. I already showed that to you in the previous video, but this video will do it even more. Further, I'm not just attacking her. I'm attacking finite element programs and the bias that you put into them. Somebody open the window for Georgie, and that you put into them Sorry about this noise in a second. Hey, George. So he needs the window open. She put corrosion added. I'm holding out on some corrosion details for you guys about not this wall, another wall. This wall had a cap on it, and so they're trying to pick on corrosion there with no identification of corrosion. In fact, it's kind of corrosion added, but then saying rebar is missing, and not presenting the photographs exactly where this rebar is missing. Just stating that it looks like rebar is missing per the photographs. Well, per the photographs, overlay the rebar that's missing. Show us the missing rebar. All right, so this is the problem with people like Don Lehman, etc., that use these finite element programs and come into it with a bias that they can't even see themselves. Her bias is she made a conclusive file that you can't judge a building, figure out how a building collapsed in its failure state. Her quotes, not mine. She shows a flap, but more than that, the video of Adriana has been excluded from her evidence. From her evidence to chicane it. Down here, her fracture line over here, and this is very critical right here, where she states, none of the scenarios based on, it's Adriana, the lady that took the video, created a damage pattern consistent with what occurred at Champlain Towers, according to the Harold/Don Lehman's models. University of Washington, she's representing University of Washington. Very interesting. University of Washington is allowing her to use their name. So what does that tell you? That tells you the University of Washington is trying to solicit for engineering school using this. Using this as a way to ride to say, come to our school. This is obviously with their knowledge, and they've got the wrong person representing them in their engineering department, earthquake department. This is what it was really about, trying to make sure your department gets a little bump. She's representing University of Washington now. This Don L. Lehman. Her. So this shows that what the real intent of this writer is, trying to pump up the schooling. All right, so there's the fracture plane. There are the columns. There's the wall, and the fracture plane. It says exact edge of collapse is unknown. Well, okay, this is what I've been waiting for. So this is where Don Lehman states that the separation took place. It says elevator core wall, pull deck, and beam and gym. This is where she has it removing. Her has it removing from the wall. You got to learn the dialect. You think, guys, I'm trolling sometimes with the she, her. It is mental evaluation of the person also that declare such themselves as such. So elevation change is what she refers to it as, and the drawings refer to it as a drop slab detail. And elevation change, and she has it shearing away from here, just breaking away like this from the gym floor. And I'm going to show you that that's not true, because it's the shear wall, and it has anchorage into there. So that is, it says inadequate connection to the wall here, is what her states. Don L. Lehman and University of Washington states. Clearly, they can't look at the imagery. She can't look at the imagery correctly, representing University of Washington. So therefore, University of Washington is terrible with their schooling, and because of their teachers. She states that there's beam twist, etc. Now I'm going to disprove this in an easy swipe of the hand in this video, in the last video also, of just straight ramp, if you will, straight. Car parking. You see the cars are here parking in this direction. They turn, they come this way, and they turn. So that's a lot of loading I talk about there. And they stop here. So the surge is here, right about that lane there. But then we have the building over here, and let's zoom in on that again. our anchor point is identified, or a hinge point is right here where it stops. You see clearly how it goes down and levels off. This is our hinge point. Our hinge point. This is where it comes to change direction and go that direction. That's in line with our planter boxes, which is, hold on, let me do this right for you. So here's a planter box in green, and that's right in line with the planter boxes. Thereabouts parallel with the outer wall. Thereabouts parallel with. I'm gonna try to get some guessing here with that wall there. Considering this wall goes all the way through, the column goes through, this column goes all the way straight down to the garage floor. Let's undo the last two. So you see that this reveals the hinge that took the hinge action on this side, and so I could argue that the stability, the stable part of the structure, the hinge, the rotation is right about here. This is the edge of the building. See the edge? Now watch what I did there, right here. I did this all freehand, and just so you know, I try not to be biased. So this video is being edited and done as I speak to you. It's a theoretical in my mind that I share with you, and I work it out in my mind, and then I see if I can confirm it or debunk it. This is actually my K column. So for this to be and then I'll erase them. So this is that head, this is the other head, and this is where the BMA went across. So if I was going to pick on anything as a shear plane, I would say this is very strong out here at this wall system. If I were going to choose a better spot, I would choose it back here, because this is where it has a 7-foot deck from this wall, from here. And an elevation change of 11 inches. So I would tap back into it. Okay. So, but at the same token, we don't have that in place. We do not have the BMA in place across here. It's gone. It's lowered down. It's lowered down, and thereabouts at the same elevation as this point here. So there's our 7-foot set off. Maybe that 7 foot is, I would need to guesstimate, and I would say there's a door. So we have a door, commercial, we have a wall. We have a commercial door presenting right here. And so that's somewhere about 4 feet, I would maybe say 5 right here. So that means this wall is, I'm going to mark in the column head here. I'm going to stay in front of it this time and make these meet. In other words, there's the column head. That's K. That's the face of the structure. We find the face of the structure here. And then we're going to call this about, say, 4 feet, 4.5 feet, let's call it. So 4 feet 6 inches thereabouts. There's no column under there, so we're going to say that reaction is a cantilever pivot point from that steel. Remember, this steel has a 1'6". Watch this. Wait for it. This has a 1'6" elevation change over here. So there's a beam here, the drop slab, and then the decking that goes over to here, all the way over to the garage that supports the cars. And this would be literally this decking here. And if you could walk out, no elevation change would be part of that. Now that's some material on top of it. We'll discount that because it didn't break it away. But so we're going back here. So our deck elevation change is all this, and it looks like that. So there's 13.6 up here. There's 11'10" down here. There are the columns with the beam, the BMAs across. And the BMA, I think the slab is all the way over to here in place, I believe. The reason why I think it's the BMA is mostly in place the levelness of the pad over here, the levelness of it out to the face where the planter box is. Now, I can get displaced materials from the building falling in and filling in the basement to some degree with the cars to help it, but the planter box, this planter box is the one that's nothing underneath of there. And let's see, planter box, nothing underneath of there, right? So that's the part of the driveway. Yeah, nothing underneath of there, so I don't have the car doing anything there. So there is where I come with that hinge point. Literally, the hinge point, the reaction point, if you will, is roughly parallel with this door. So then we go to the plans, and I won't do it in this one, and we look at our hinge point, and we evaluate the steel that goes over, including the drop slab detail. And why did it make it approximately 4 feet, right here, 4.5 feet in strength before it said, you know what, you can fall down, but this is where I draw the line right here. I am strong enough to resist the forces of you trying to tug on me any further. I am strong enough. Part of that is it's a two-way directionally supported system. This wall is anchored this way. The shear plane is coming across in this direction. And so now you don't have the tugging action pulling away from the wall here. So you've got less tugging going on. The two-way pulling this direction and that direction is equalized here from the corner of the structure. Equilibrium. And it's equalized out here. I know that because we're looking at it. It's not equal. It didn't have enough ability to keep going back, unzipping it back to here. This is where it met its equilibrium with the forces, where it came to rest. So rest stops it from having any more energy. So this is where the bottom of that drape hits. It has no more tugging ability. And this rest is why it doesn't come up any further than right there. Not because of the, I know I give and I take, not because of the BMA and a cantilever effect. And I started this video off talking about rest. I showed you how I play devil's advocate, playing both sides of cantilever and this and that. But ultimately, it's because of rest. That once it becomes at rest, it loses its energy to continue ripping and tearing down the building. But the tugging action that took place over here has already, and per the video now per the video we see of the nighttime vision of the collapsing, that indicates that column did some, the M column of the building had some failure mode. The M column. I choose the M, and then I also choose that the building rattled. See, and that's where I can have, I can go a couple of ways with this. The rattling of the building caused the top floor to this top floor, the 10th floor thereabouts. It's 12 floors, right? So about the 12th floor thereabouts, well, to the above like 611 and 711 stack. That stack there, the C stack, and the C structure, the C apartment buildings that go all the way up, and we have some data to support that from 611, where she turns to the right and she sees a two-fingered, what she describes as two fingers being able to fit into the crack. I believe that's the front of one of these sausages, pulling away from the structure. So sausage, here's a floor in between them, creating what I call these little sausage links. And when a building rattled, one of these sausage links separated a bit, and she's able to stand here inside her room